Hey, this is Uwe. I'm CTO of Image Engineering, and welcome to the session Color and Spectral Sensitivity. So, what is color? Color is basically a human perception. And this human perception is formed by three components. It is the spectral distribution of the light. It is the spectral reflection of the object, and it is the spectral sensitivity of the observer, for human eye. So color is a complicated topic, and also the processing behind it in our brain is different. But we can use the so-called color matching function as a good model on how a human perceives spatial content, or so the different parts of the spectrum. So that gives us the X, Y, Z values. So that means we can calculate or describe a color as X, Y, Z values, and they are mathematically created as an integral over the wavelength from 380 nanometers to 780 nanometers. So integrated with d lambda and multiplied the spectral distribution of the light source, the spectral reflectance of the object, and the color matching function of the human eye. So that means we can have an object, so a color patch, for example, we can illuminate that. And if we know all these things, we can calculate the XYZ value for that. And with that, we have described the color, how a human would perceive this color. So what does the camera do? Pretty much the same. So to calculate the RGB value in case of an RGB camera, you also integrate over d lambda or over lambda in the visible range, and you multiply the spectral distribution of the light source, the spectral reflectance of the object, and then the spectral sensitivity of the camera. So that is basically what gives you the RGB values. So that also means that if with variation in the spectral sensitivity, you get different RGB values. So every camera has a slightly different spectral sensitivity. Different types of cameras might have a huge difference, but even the same model on production line, so one camera to another, will have slight variation in spectral sensitivity. So they all will give you slight variation in the RGB value. And if you have a huge variation in there, the user will have a bad experience. You get off colors because your processing is not tuned to it. So if the sensor has some variation, but the processing does not know about it, you have a bad user experience. So that's why you want to calibrate colors on production line. And we show you now here how to do that. So one method to do that is the chart-based method. So as the name suggests, you use a test chart for that. So it's a very simple approach. You take a test target. So for example, a color checker test target. You illuminate that, and then you capture an image with the device on the test. And that gives you the RGB values for these color patches for this light source. And then you can do the same to get the XYZ values. So basically you take a measurement device to measure XYZ values directly from these color patches. And then you have the combination. For every patch, you have a pair so that you have RGB values and XYZ values. So then what you want to obtain is a matrix that does the conversion from your RGB values to the XYZ values. You will later on go from XYZ to like sRGB or Rec 709 or some other color space. But the core calculation is to go from RGB camera to XYZ. And for example, with a 3x3 matrix. This so you have the XYZ can then be considered as device independent because it will be a description of the color independent from the camera that has it. And the RGB is device dependent, but also the matrix is device dependent. So the camera will give different RGB values, so the matrix will be different. So how does that look like? Yeah, so as shown here, you capture a test target with your camera under test. That creates your camera data. And then you take a suitable measurement device that measures each of these patches, XYZ values. So that gives you the training data. And then you have, so in this equation, you have T and you have C, and you're looking for M. So that is a mathematical problem that you need to solve. Most likely what you do is that you first do a linear estimation first, and then have some further optimization where you iterate over it to give you a 3x3 matrix. What's the problem with the chart-based approach? I mean, a lot of people do that, and it's a relatively easy approach. The thing is, you measure the RGB of your camera, and the spectral sensitivity of the camera remains unknown. And you have to take the patches of the target and the light source as given. So that means the 3x3 matrix that you obtain is then optimized for the light source that you used and for the target that you used. And of course, if you use, for example, the color checker, you have 24 patches. 6 of them are neutrals and others are extreme. So you don't have enough colors to really represent real life. So you optimize for color checker patches, which do not really represent reality. So there is a better way to do that, and that's a spectra-based approach. So instead of measuring RGB and using the target as you have it, you can do it that you measure the spectral sensitivity. And then you can calculate RGB based on intended simulation data. So you can then just measure any light source or define some light source, but also just take some data of objects. You don't have to bring them into a production line. You don't have to bring them into the lab. You can bring, for example, if you use the in situ database, that's an image engineering product, you have 2,000 objects. Skin tones, color, flowers, so many different objects measured really in situ, so on the living object. So you can bring all these into lab, but once they are measured, you can calculate or optimize your color conversion with that. So how to do that? Basically, it's the same approach that you use RGB and XYZ pairs for specific colors, but it's not that you take them from a color checker. You just take from your database. You just optimize that with the tools that you have, so that you define a light source, you define objects, and then you calculate the RGB with the spectral sensitivity of the camera, and you calculate XYZ with the color matching function. So what are the trade-offs? So the chart-based approach, yes, it is simple, fast, and easy. So you need a color checker or a color target, some lighting, and you can do that. So for a simple approach and academia and so on, you can do that. But of course, if you want to create for a high-end device or a proper device, that might not be suitable, because the transform domain, how you create your transform is basically limited to the gamut of the target that you used and to the capture conditions. So basically you optimize for a color checker, but frankly speaking, I haven't seen a color checker outside the lab. I mean, colors in real life are different. The blue sky is different than the blue in a color checker. The green grass is different than the color checker. So you should optimize for that. The big benefit is if you want to, and in many cases you really want to, optimize your color correction matrix for different illuminants. So you want to have a different 3x3 matrix or conversion for an warm indoor light compared to a daylight outdoor, or to to your own light source that you bring with the camera. You want to have different conversions for that. If you use a chart-based approach, you have to have these light sources actually in the lab or in the production line to do that, to optimize for that. And that's a hassle. Having many different light sources in there, it's really a problem. So with a chart-based approach, with a spectra-based approach, you actually just do that mathematically. So you measure spectral sensitivity, and then you can calculate for as many combinations as you like. The other benefit is if you use a spectra-based approach, you are actually very well prepared to do some more sophisticated conversions like multidimensional lookup tables. So I made the example with the 3x3 matrix, but that is really the most basic approach to do that. Modern color processing is often done with multidimensional lookup tables. And if you want to do that, you actually need much more colors. You need to optimize for that. So then the spectra-based approach is your choice. So the only negative side that you have on the spectra-based approach is that you actually need to measure spectral sensitivity on production line, which sounds terrible, but it is easier as you think. Just a hint about, I already said there is the in situ database. So image engineering offers the in situ database and bundles actually it with the ChemSpecs product range. So there you have real life data. So we went outside and measured many objects, trees, leaves. We asked many volunteers, people, to donate their reflectance of their skin. So we asked them, hey, are we allowed to measure your forehead or your cheeks? To put it into a database, and many people volunteered. So we have this database, and it's part of it's a standalone product, but it's also part of other products, so that you can get access to this database and make better color conversions. So how do you actually measure spectral sensitivities? So the gold standard, so very accurate, is using a monochromator. The thing is, a monochromator is not a cheap device, and monochromators are made for labs. They're not made for production lines. So they will wear out very quickly. The motors are just not made for that. So you can test prototypes with a monochromator, but you don't want to do that on production line. A very good approach to do that is a filter-based system. So what you see here is a product that's called ChemSpecs Express. So basically, that's a halogen light source that back illuminates a set of 39 narrowband interference filter. So that means the device on a test captures an image of these filters and has then 39 measurement points. So from that, we can directly calculate the spectral sensitivity. So one shot, and you have your spectral sensitivity. The ChemSpecs Express is, as I said, designed with a halogen bulb. So that's, and comes with a calibration device so that you can recalibrate, every now and then, specifically when you have to change the bulb or if the bulb ages over time. So that's why production line might not be the best environment for the ChemSpecs Express. It's great for lab and, for small volume production lines, but for high volume 24/7, it might not be suitable. But for that, we have now the ChemSpecs plate. So that is the same filters as you have in the ChemSpecs Express, just mounted that way that you can put them into an LE7 light source. The LE7 is based on the IQ-LED technology, and so it is really made for production line. So it's stable, it can recalibrate itself and so on. So with that setup, you can really go on production line and test with a single shot the spectral sensitivity. So basically, how does that work? So we have like a monochrome output from these filters. The camera captures these, and together with the calibration data, so with the knowledge about what is the exact spectral range of each filter, so how wide it is, what's the peak wavelengths, and so on. This data together, we can directly calculate the spectral sensitivity in 10 nanometer steps and then interpolate them into even finer if we need to. So yeah, these are the different filters that you can use for that. So, or that we use in the ChemSpec. So that's a direct measurement. You capture a raw image, so it's highly recommended to use raw data for that, or it's a requirement. No problem on production line with that. You capture these images, 39 filter, and then you have a software so that you can get the spectral sensitivity. Based on that, you can calculate ICC profiles in the software or do your own further calculation as you would do on production line. If there is help needed, we do have experts for that can provide consulting how exactly to implement these things. If you already have an IQ-LED light source or thinking about to integrate an IQ-LED light source on your production line, also with that, you can do a spectral sensitivity measurement. And that's extremely powerful because the IQ-LED light source, calibration light source, can then be used for many, many different things. So you do with the same light source, you do a shading, a gain calibration, you do defect pixel detection, but then white balance and so on. But you can then also do the color conversion calibration or the spectral sensitivity calculation. And we do have a technology for that. So basically, we need to build a database of devices to create some prior knowledge. So typically what you would do, you take like 15, 20 devices from a pre-sample, from a pre-phase of production line. So when you ramp up, you measure them, do a direct measurement, for example, with the ChemSpec Express device, create this database. And then on production line, you have the IQ-LED device and your device on a test. So that device on a test will capture images from the IQ-LED device, changing the colors. And together with the database, that all goes into the API or into available API, and that will output your spectral sensitivity. So what we need for that is basically 22 different images that are the 20 channels of the IQ-LED plus a black plus one like D65 white. So you can obtain these images in some seconds, so that you can really and can synchronize everything with the IQ-LED devices and so on, so that you can really capture these 22 images in some seconds, and then perform the analysis so that you can go and have in like less than 10 to 15 seconds have a spectral sensitivity per device. So how does that look like? Basically, your DUT, so your device, will capture images while the calibration device will change its color channels. So that means that you do this 21 times plus a black, store the images, provide them to the API, and it will then do the calculation. Okay, and that will give you the spectral response, and then further on based on that, you can do calculations, optimization to get your correct color conversion. Okay, thanks a lot for listening. I know a lot of details. Our team is very happy to provide more or answer questions, provide more details and do consulting on that. But I think you get the idea that IQ-LED, ChemSpecs, and our expertise is very valuable for your production line needs. So thanks a lot for watching.